the sound here because it's echoing. Okay. So the last time I did this, I had to redo the reading of the files and converting them to H5ADs because I made a mistake in which file I was reading. So now, since then, overnight I converted all of the txt.gz files to H5AD files. So now what I want to do is I want to add the annotated coordinates for the beads in these H5AD files, and then I want to combine them into a single file so I can easily make a plot with a single file for the original Slide-seq data. So I need some helper packages, but of course what I need the most is the undata package so I can read the files. And I'm splitting it up to a different notebook from the original notebook because I want to keep this separate. And my idea is that I will put a directory with all of these notebooks on GitHub when I'm done. And then I guess in theory people can look at the notebooks and follow how I arrived at the plot I will arrive at the end. So just to check one of these files, I'm going to load one of the pucks. Oh yeah, and it even has the file name annotated, that's nice. We will be able to use that later to add annotations. Yeah. Let's see. So the corresponding locations of the beads is in this locations.csv file. So if we just look at that, we have the barcodes here, which are the same ones for whatever is in this data object and is in this CSV file. So say that we have a file name. Then this is the same, but we're just replacing this part with this other part. So name.replace. Oh no, I forgot what it was called. And I know that these obs are just going to have X chord and Y chord, so I'm just going to add them directly to the obs object in the A data frame that I already have. Okay, so now we have the X coordinate and the Y coordinate and the file name in this structure. And this should be consistent across all of the files. So I just need to change this into a loop. So first, to put all of the data in a list, and I append each data in this way to that list. And this pattern will let me read all of the A5AD files I already saved. Just to be sure that it's future-proof, I'm going to add a little specific identifier like this. I'm just going to check that this gives me what I think I want before I start reading everything. Yeah, so this gives me how many? Should be able to check easily. This gives me the 9 pucks that were there, and I can add them. So 4. And this together will add the X coordinates and read all of these data files. So let's look at the RAM. Forgot task manager. Yeah, keep mixing up the Mac names and the Windows names for these things. Okay, so something is wrong. And it's with the observations. So why is this? We have a file name like this, and so puck20 oh, there's something wrong here. No, 200115. 200115 08. Yeah. But somehow it doesn't have the B locations, is what I'm guessing. So if we just try to read this one file, yeah, don't know actually what's wrong. Oh, the difference is in the very last one, it's tab separated as opposed to like the first row is tab separated, I think. Let's open this. Let's see. It's this one. Open with code. So this one, yeah, this is weird. If I look at either of the other files, like this one, that one has the header the way you would suspect it to be, but for some reason the first row here is tab separated as opposed to comma separated. So I just fixed that. It's kind of weird that the data is like that. But now I have everything. So this ADatas list has a list of these different ANData files or ANData objects, and we have these different. So if we look at the first one, which is the one we've been looking at all throughout this, it has 33,000 beads and 22,000 genes. So we can see that the number of genes differ quite a bit between the different pucks that they have deposited data for. Yeah, and that's just kind of what happens, I guess, because some of it will capture more genes than the other, and you don't want to save all of the genes that you only have 0 counts for. But what we want to do now is we want to concatenate these. So now we should have a single file, yes, which have a batch ID and a file name. The file name should match whatever is in the batch. And you see we have fewer genes now because by default this method takes the intersection of the genes. So I think, well, in order to read the documentation I have to look at a single object. So I'm going to change this join to outer. That means that we're going to get all of the genes which are present in all of the pucks, and that way we're not throwing away any data. This takes a bit longer, but because I think it has to make new matrices for everything now that has a larger dimensionality than otherwise than the individual matrices. It's easier to kind of slice the small matrices to match up, but now it has to make a new larger matrix that has all of the genes in it. Now I thought I had written down some annotations for which puck came from which puck came from which tissue or things like this, but I don't see that. Because I would like to add that directly to this file so I have it in the future. But I suppose that's in the paper. So here's kind of an index of what the different things are. $21.19. Okay. Mouse E15 brain. So 2121. It's mouse hippocampus. $26.09. Can't figure out really what this is. Supplementary table 7. Yeah, it doesn't really say what this is. So I presume that's the same for the 2602. Yep. Okay. Then the next is 2606. And that's also one of these that we don't know what it is. Yeah, that's unclear. And so 2606, 0707. That is not even mentioned. I wonder if it's possible to just look at the data and figure out which tissue it's from. So where were we? 0707, 0401. for 1 we have this final one, the 1508. So then we have some annotation. So and now the data combining is done as well. So now we have a single data object and data object which has 389,000 beads and 27,000 genes. So we should be able to use this for any analysis in the future. We can just slice this for whichever genes or data we want. So now I want to add this tissue annotation to it as well. So in the obs, I save this file name. So what I don't want to do from that, I want to extract. I want to extract the first bit of the file name before the .digital gene expression, because that's how I annotated the tissues in this little mapping. So with pandas, you can, if you have strings in a column in pandas, you can use this little string getter, and then you get access to a bunch of string functions for that column, which is very handy. So now I can split it by the full stop symbol, and the list also kind of behaves like strings in a way. So I can get the first object. So then I get the first string before the dot. And then I just map the tissue. Well, I should probably move this to be above. And now we get all of the tissue annotations. So then we add this to as a new column in the observation data frame. So now we have all of the data in one object which has x coordinates and y coordinates. Within it, it only makes sense to plot them, of course, for a single puck. But we can find that using either the batch thing or the file name, which actually relates to which actual sample it was. And we can query this by which kind of tissue we want to look at. So it's nice. We now have this size, so we now know how many beads was in this experiment in total, which I like using as a kind of sample size thing. But I'm going to write this now too. So this is all of the Slide-seqV2 data. I don't like having those. Okay. Actually, and who's the author of this paper? So then I just have all of the data like this. It's not very small, it's about 1 gigabyte, but we only need to deal with this one file, and it actually is pretty fast to read. So now when I've done this, actually what I'm going to do, because I didn't know this number before, I'm going to add that number to my spreadsheet of experiments. So this is the single cell RNA-seq database, and we have this entry here for the Slide-seq2 paper. We have that it's mouse, we have some stuff, but I didn't know how many beads were used, but we know now. It's 389,037. Great. Well, but now we combine the data. We have everything we need. I don't need to look at this anymore. I can remove these other plots. Okay. Oh, what happened? Alright. So since we have that file, I'm going to make a new notebook with the same stuff. So I'm going to call this, I'm going to load this data as Slide-seqV2. Sorry, stick. Right, so that's the file name. And somewhere I have the Slide-seq data. I definitely have the hippocampus, so that's what I want to compare. So I'm just going to copy this. So that's version 1, Slide-seq equals and then let's see. So in Slide-seq we have 1.5 million beads, while in Slide-seq2 we have this many beads, about almost 400,000. Okay, and I guess these are all from hippocampus, so they should all be comparable. It's just a lot of dots. It's going to be annoying to plot, but well, whatever. But because I know that this Slide-seq data is from hippocampus, I'm going to actually slice this data to only look at hippocampus. So in the observation we have the tissue. Let's see, what's a good way of doing that? Tissue dot no, that doesn't work. It's too bad. Okay, what we do have tissue You can treat this as a string again. Contains. Yep. Okay, now we have mask. So slide. Well, actually, let's first check if this mask works. So the Slide-seq is, or this andate object is by observations first, so we should just be able to put in the mask like this. Yeah, and then we receive a smaller thing with only 100,000 observations. So I'm going to make a new, I'm going to copy this as well, called hippocampus, because this should be comparable between the two datasets. That is right. And what do I want to calculate? I want to calculate. So let's do this for the Slide-seq version 2 data first, because it's going to be quicker because it's smaller. So in this we have the X, which is the gene expression matrix, a sparse matrix. So the first identity I want to calculate is the total number of UMIs measured per bead. And we can get that by doing sum. This, I think I always forget about the dimensions. But if this is 100,000 or so, that's the, yeah. So this is the sum across all genes for every bead. Now it is in this matrix format, and we actually want it to be an array. And then once it's an array, we actually want it to be a vector array. And then we can add this as a feature, or as an annotation for the observations. So then we have that. The next thing I want to calculate is how many total genes were detected in a given bead. So if we look at this code here, it's just taking the values that are in the matrix and it's summing them. Instead, I'm going to make a binary new matrix that checks whether the entries are larger than 0, which is a very quick operation for sparse matrices, and I'm going to sum those. So now we actually get the number of detected genes, the unique genes which are detected, not like the copies of them, just whether a gene was ever counted or not. And I just like having this as a single block. I can just run it, and now if we look at the data, we have these values here. So what we want to do is we want to do this as well for the Slide-seq data. The Slide-seq data, of course, is much larger, but because we're storing this as a sparse matrix, it should be pretty quick to calculate. So we just replace the Slide-seq2 with Slide-seq, and it's done. So that way we were able to calculate all of these things for this large 1.5 million data sets. And yeah, that should be it. So now I just want to plot this. So normally I will plot this using plot9 because I like doing that. But because this dataset is so large, I'm just going to use base matplotlib, which is a lot faster. So from the observation, I want on the x-axis the total counts. And something that always works best is to log the axis before making the plot. And on the y-axis I want detected genes, but from the same data. And then I want to do the same thing for the Slide-seq2 data. Hopefully this will work. Oh, yeah. I wanted, of course, the detected genes to be on the y-axis. Okay. It really looks very similar. It really looks like there's pretty much no difference between them. Well, that's a good thing to investigate. So I'm just going to put in a lot more annotations and things like that. So first of all, I want the figure to be larger. Make it 12.8. That's in inches, I think. And to save some time, I'm just going to prototype it using the version 2 data because it's so much smaller. I want the labels, so I know that this is Slide-seqV2. And might add this here as well. Should probably add the citation. I think that's like a good way of keeping track of what is what. Of course, I don't remember the author of the Slide-seq paper. Let's do it like this. Slide-seq. It's Rodriguez. Okay. Like this, and then the Slide-seqV2. That's Stickles, I think. Yes. Right, so I'm going to name this as well. That's a good idea. 2005 straight through 3 comparison plot. Okay, I'm going to manually set the color to red for version 2. Though I like dark red. No, it's red. This is actually getting busy, so I like splitting things up. So I see all of the options. Always forget the option for adding more points in the scatter plot. been a long time since I used matplotlib. Yeah, this is what I want. Ah, that's weird. I can't remember for the life of me how. Legend. Oh, it's just scatter points. Okay. Yeah, that's what I want. And I want to remove the spines. Actually, I want this to be black. Okay. This should be it. Should be the final plot. Yeah. So, as far as I can tell, there really is no difference between these two datasets. There's a more, you can see more spread for the Slide-seq data, but also it has, what does it have, like 5 times as many beads, so there's no reason to not expect dots to be outside of the range spread by the Slide-seqV2 dots. Okay, I'm just going to try to make this a little bit easier to see. I'm going to make smaller markers. And just define their size. Let's equals, say, I don't remember, 10. Oh, 3. yeah, you might be able to argue that that Slide-seq version 2 is kind of on top or like above values for Slide-seq. But actually what I will do is I'll make the same plot again after this, but just sort it the other way around. So now it will plot points from Slide-seqV2 below the Slide-seq1 points. And then we can see if we can see the Slide-seqV2 data peaking out. But I don't think so, because I think the upper limit here is just like a theoretical upper, or it's based on just sampling theory from a multinomial. Yeah, okay. From this you could argue that there is a slight increase, but it's very slight. And it's for a very small population of cells. Actually what I really should do, just to avoid confusion, is add labels to the axis, which is easy to forget when you make the same plot every day. And I have the what's it called? A title as well. Then I'll just do this for the inverted plot as well. And of course what we could do, just to be a bit more quantitative than just looking at this plot, of course it all depends a bit on how the data was generated. So I would generally expect if you just take the Slide-seq data and sequencing it deeper, you will end up moving things. And of course this data doesn't tell us how many reads there were that went into the UMIs. So if you need fewer reads to get the same number of UMIs, that is more efficient. But it would have been nice if they had sequenced both the dataset to the same level, which I don't know if they did or not. I haven't really read the paper carefully enough to see that. But yeah, everything here needs to be normalized by the sequencing depth. That's kind of the thing. It is clear here that yes, they might have achieved the same kind of data quality using a cheaper sequencing depth. But it's not super clear here if that was the case, because just looking at the data alone, the data looks very similar. But for the sake of everything, we have these observations. So what I'm going to do is I'm going to take these two columns, And let's just look at the mean of those. So for the Slide-seqV2, we can see on average 500 total counts and an average of 351 detected genes. While the Slide-seq data, yes, it's much lower. Yeah, definitely much lower. Okay, so that is good. So there is like an increase here. That is something we can actually add. Actually, this might be a nice way of illustrating things. I just want 1 point for it actually. So this point is going to be Slide-seqV2. This X, Y. Just gonna check what that looks like. Yeah, okay. For the Slide-seq data, there's a lot of mass down here. While for the Slide-seq2 data, the mass is up here. So it is definitely better, by far, on average. Wonder if I can make a nice way of showing this. Yeah, let's see. So this is the Slide-seq. I want this to be, because Slide-seq is black. Let's make this white. No. Let's just keep it like this. Yeah. want to separate this from the other things by making them, let's make them into plus. I want them to be a lot larger so they're easier to see as well, because that's kind of where the main point is. Yeah, I think that's pretty good. So how many more counts are we getting in Slide-seqV2 versus Slide-seqV1? Yeah, okay, so it's about 6 times more. On average. On average it's 6 times more UMIs per bead, which is a big improvement. It's just it's not to the level of single cell RNA-seq. It's even for this red mass, it's about 1/10 of what you normally get from a single cell RNA-seq experiment. So it could be nicer. Obviously, like with the Slide-seq, every single cell is covered by multiple beads. So when you sum up the beads, you might end up having at least 10 beads for a cell. So you might have the same quality, but it's going to be harder to analyze this kind of data compared to single cell RNA-seq data. Okay. I actually want this to be a different color. And the reason for that is that way I can make a version of this plot for the other plot order as well. It's okay. I should change this to be C3. I think it will be slightly easier to see the contrast with the C1 color in that case. I think so. It's a bit easier to see. Okay. But then we have the final plots. So that's what I wanted to check. Yeah, that's about it. So what I'm going to do after this is I'm going to make a GitHub for these things, add these notebooks there, and I'm also going to figure out where to put some data, and then I might just write a very short blog post on the result of these figures, like super short. But I'll also just post these 2 figures in the tweet that I announced the stream in. And yeah, that's about it. I finished what I was thinking it would take a very short time, but then saving the data took a lot of time. But now we actually have this nice data frame that I can reuse for any other kind of analysis. Right, that's it.